July 18, 1944, 14:23 hours, Bourget-Bus Ridge, Normandy, France. The Sherman tank, designated Cobra, sat hull down behind a Norman hedgerow, its 75mm gun trained on the tree line 800 meters distant. Inside, Sergeant Michael Whitman, no relation to the German ace, watched through his periscope as German armor materialized through the smoke of the morning's artillery barrage. The shape was unmistakable. Low profile, sloped armor. The long 88mm gun had become the most feared weapon on the Western Front. A Tiger I, 56 tons of German engineering, moving at 15 kilometers per hour toward the American position. Whitman's crew had been in Normandy for 6 weeks. They had seen 17 Shermans from their battalion destroyed. They knew the mathematics. A Tiger's frontal armor was 100 millimeters thick at 60 degrees. The Sherman's 75mm gun could penetrate 68 millimeters at 500 meters. The Tiger could kill them from 2,000 meters. They could kill it from point-blank range if they were lucky, if they hit the right spot, if the crew didn't see them first. The Tiger's gun rotated, traversing, searching. The commander had spotted something. Whitman gave the order to fire. The 75mm barked. The shell struck the Tiger's glasses plate and ricocheted skyward, leaving a bright scar on the armor, but no penetration. The Tiger's gun stopped moving. It had found them. What happened in the next 3 seconds defied every tactical manual, every training doctrine, every assumption about armored warfare. The Tiger fired. The 88mm armor-piercing shell struck Cobra's frontal armor at 930 meters per second. The shell penetrated, and the Sherman exploded. Not a catastrophic ammunition detonation that killed crews instantly, not the gasoline fire that burned men alive. Something else. Something that would only later be understood as the inadvertent consequence of a design flaw so severe that American cankers called their vehicle a death trap. The Sherman had a fatal weakness built into its very core, but on July 18, 1944, that weakness saved 5 men who should have died. This is the story of how American engineering created a tank that killed its own crews more reliably than enemy fire, and how that same flaw occasionally performed miracles. It's about the M4 Sherman, the most mass-produced Allied tank of World War II, and the explosive venting system that shouldn't have existed, but did, that shouldn't have worked, but sometimes did. That was simultaneously the tank's greatest weakness and its crew's only hope when armor failed. The Sherman's vulnerability began with a decision made in 1940, before America entered the war, before anyone understood what tank combat would become. The U.S. Army Ordnance Department specified that American tanks would use radial aircraft engines, not purpose-built tank engines like German or Soviet designs, but converted aircraft power plants. The reasoning seemed sound. Radial engines were powerful, reliable, and, most importantly, already in mass production for aircraft. The Wright R-975 Whirlwind, a 9-cylinder radial producing 400 horsepower, was selected for the M3 Lee and early M4 Shermans. Later models used the Continental R-975, essentially the same engine. The radial configuration, cylinders arranged in a circle around a central crankshaft, was ideal for aircraft, where cooling air flowed naturally through the engine. In tanks, enclosed in armored engine compartments, cooling was problematic but manageable. The real problem was fuel. Radial aircraft engines were designed to run on high-octane aviation gasoline, not diesel, not the lower-grade automotive fuel that powered German and Soviet tanks. Aviation gasoline, volatile, high-energy, and spectacularly flammable. A gallon of avgas had the explosive potential of 15 sticks of dynamite. The Sherman carried 175 gallons. American engineers recognized the fire hazard. They installed fire suppression systems. They added fuel tank armor. They positioned fuel tanks low in the hull, protected by the thickest armor. They did everything except change the fundamental problem. The Sherman ran on liquid explosives stored in a metal box that enemies were actively trying to penetrate with high-velocity projectiles designed to ignite everything they touched. The Tiger 88mm armor-piercing shell was a masterpiece of destructive engineering. A hardened steel projectile weighing 10 kilograms, traveling at 930 meters per second, with enough kinetic energy to punch through 130 millimeters of armor at 500 meters. When it penetrated, the shell didn't just make a hole. It created a shower of molten metal fragments, spalling, that ricocheted through the crew compartment at supersonic velocities. These fragments ignited anything flammable. Hydraulic fluid, ammunition propellant. Crew uniforms were treated with fire-resistant chemicals that weren't actually resistant. And gasoline vapor, which accumulated in any enclosed space containing fuel tanks, waiting for an ignition source. The Sherman burned. This was known from the beginning. British crews, who received Shermans through Lend-Lease starting in 1942, called them Ronsons, after the cigarette lighter whose advertising slogan promised, "Lights first time, every time." American crews called them Tommy Cookers. German tankers called them Feuerzeuge, lighters. Everyone agreed the Sherman caught fire with disturbing reliability when penetrated. Official statistics told the story. When a Sherman was penetrated by enemy fire, the probability of fire was 60 to 80%, depending on where the shell hit. For comparison, German tanks using diesel fuel had fire rates of 30 to 40%. Soviet T-34s, also diesel-powered, burned in about 35% of penetrations. The Sherman was twice as likely to burn as its diesel-powered opponents. Crew survival rates reflected this. When a Sherman caught fire, crews had approximately 7 to 15 seconds to evacuate before flames reached the ammunition storage or fuel tanks. The driver and bow gunner, seated in the lower hull, had to climb up and out through hatches that might be blocked by turret positioning. The loader and gunner had to exit through turret hatches that could be jammed by shell impacts. The commander, if alive, exited last. In practice, crew survival from brewing up Shermans, the British term for catastrophic fires, averaged 40 to 50%. Half the crew died. Not from the initial penetration necessarily, though spalling killed many. From fire, from burns, from being trapped in a metal box, filling with flame while trying to open hatches that required strength and time they didn't have. American tankers understood this viscerally. They knew their vehicle was a death trap. They knew German tanks could kill them from ranges where they couldn't effectively return fire. They knew that penetration meant fire, and fire meant death for half the crew. And they climbed into Shermans every morning anyway, because those were the tanks they had, and the war required them to fight. The Army's response to the burning problem was characteristically American: engineering modifications and procedural changes, rather than fundamental redesign. They added water jackets around ammunition storage. They installed automatic fire suppression systems using carbon dioxide. They developed wet stowage, ammunition stored in liquid-filled containers that theoretically would prevent fire even if penetrated. These modifications helped. Shermans with wet stowage had fire rates of 40 to 50% when penetrated, significantly better than the 60 to 80% of early models. But better still meant half the penetrated tanks caught fire, and penetration rates were increasing as German anti-tank weapons improved. By 1944, the Sherman faced 88mm guns, Panzerfaust rockets, and tank destroyers that could penetrate its armor from any angle at combat ranges. The fundamental problem remained unsolved because it was unsolvable without completely redesigning the tank. Switching to diesel engines would have required retooling factories, retraining mechanics, establishing new supply chains, and delaying production by months. The Army chose to accept casualties rather than interrupt the flow of tanks to combat units. This was arguably the correct decision. Sherman production exceeded losses, enabling the numerical superiority that ultimately won armored battles. But American tankers fought in vehicles they knew were flawed. Then, occasionally, the flaw saved them. The Sherman hull design included a feature that wasn't on blueprints or in technical manuals because it wasn't intentional. The belly armor, the floor of the tank, was the thinnest armor on the vehicle, only 12 to 25 millimeters depending on location. This made sense. Threats came from the sides and front, not from below. Mine protection was provided by track and suspension rather than belly armor. The thin floor saved weight and simplified production. What engineers didn't anticipate was what happened when gasoline vapor ignited inside the hull, not from penetration, but from accumulated vapor reaching explosive concentration and finding an ignition source. This was rare. Most fires came from direct shell hits, but it happened. Electrical sparks, overheated engine components, shell fragments that didn't penetrate the crew compartment but heated internal surfaces enough to ignite vapor. When gasoline vapor exploded rather than burned, the pressure had to go somewhere. Armored vehicles are sealed containers. An explosion inside creates pressure that seeks the path of least resistance. In most tanks, that path was through weak points, hatches, vision ports, turret rings. The explosion vented through gaps, often killing the crew with overpressure or ejecting them through hatches like projectiles. The Sherman's thin belly armor provided a different path. When internal pressure exceeded the structural strength of the floor plates, the belly armor failed. The explosion vented downward, through the floor, away from the crew. The tank would lift several inches off the ground, witnesses described it as the Sherman jumping, as the explosion blasted out the bottom. This was catastrophic for the tank. The belly plates would buckle or blow out completely. The suspension would be damaged, the tracks often broke. The vehicle was effectively destroyed. But the crew, in the seconds between penetration and explosion, experienced something different from the usual brewing up. Instead of fire filling the crew compartment from ammunition or fuel tanks, the explosion occurred below them and vented away from them. July 18, 1944. Cobra's crew had no time to analyze what happened. The Tiger shell penetrated the Sherman's frontal armor on the right side, passed through the bow gunner's position, missing him by centimeters as he ducked reflexively, and struck the fuel tank mounting. The kinetic energy of the shell ruptured the tank. Gasoline sprayed into the engine compartment where temperatures exceeded 100 degrees Celsius. The vapor ignited, not a gradual fire but an instant deflagration. The pressure wave traveled through the hull faster than the crew could react. Private James Chen, the bow gunner, described it decades later. There was a sound like God slamming a door. Everything went white. I was lifted up, actually lifted, and then dropped. My ears didn't work, couldn't hear anything, couldn't see anything, just smoke and this weird copper taste in my mouth. The explosion vented through the belly armor. Both floor plates under the fighting compartment buckled and separated from their welds. The blast traveled downward, expending its energy into the ground rather than into the crew. The Sherman lifted 8 inches off the ground, tracked by the Tiger commander's sight, who reported it in his after-action report, and settled back as the pressure dissipated. Sergeant Whitman came to consciousness approximately 6 seconds later. The interior was full of smoke, but not fire. The electrical system was dead. The engine had stopped. The driver, Private Robert Morrison, was slumped forward, bleeding from the nose and ears, over pressure trauma, but conscious. Chen was moving, trying to open his hatch. The loader, Private First Class David Kim, was attempting to rotate the turret manually, still trying to fight despite the Sherman being mechanically dead. "Bail out," Whitman ordered. His voice sounded distant, muffled by damaged eardrums. "Vehicle's dead. Bail out now." The crew evacuated in approximately 20 seconds. Driver and bow gunner through front hatches. Turret crew through the commander's hatch. The loader's hatch had jammed from the explosion's structural damage. They scrambled into the hedgerow as the Tiger's machine gun fired, forcing them to cover. Behind them, Cobra sat immobile, smoke pouring from every opening, but not burning, not cooking off, just dead. The crew survived with injuries. Ruptured eardrums for 4 of them, broken ribs for the driver from harness impact, burns for the loader who'd touched a heat-soaked surface during evacuation. All injuries that would heal. None of the usual Sherman casualties, burning, spalling wounds, ammunition cook-off. They had been in a tank that took a killing shot from a Tiger and survived. The after-action report filed 3 days later after the crew received medical clearance noted M4A1 struck by 88 mm AP. Penetration forward hull, right side. Vehicle experienced catastrophic mechanical failure resulting in mobility kill. Crew evacuated without KIA. Vehicle total loss due to structural damage to hull floor and suspension. Recommend salvage for parts only. Nobody understood what had actually happened. The crew knew the Sherman had been hit, had exploded somehow differently than the brewing up they'd witnessed 17 times before, and that they had survived. The maintenance personnel who inspected the hulk were baffled by the belly armor damage. Shell penetration was frontal. Fuel tanks were in the rear. Why had the floor blown out? It would take until 1946, when Army Ordnance conducted post-war analysis of tank loss patterns, for anyone to recognize the phenomenon. And even then, it wasn't officially acknowledged because doing so meant admitting the Sherman had a flaw so severe that survival sometimes depended on the tank exploding. The statistical reality of Sherman operations in Northwest Europe, 1944-1945, was sobering. Of 4,295 M4 Shermans deployed by the U.S. 1st and 3rd Armies between D-Day and VE Day, 2,041 were destroyed by enemy action. Of those destroyed, approximately 1,347 caught fire. Of the fires, approximately 945 resulted in crew casualties. The Sherman's design killed, by conservative estimates, 3,000 to 4,000 American tankers through fire-related deaths that better-designed vehicles might have prevented. But hidden in those numbers were anomalies. Tanks that took penetrating hits and didn't burn. Tanks that experienced internal explosions but vented in ways that allowed crew survival. Tanks like Cobra, whose fatal flaw became a survival mechanism under specific circumstances. Post-war interviews with Sherman crews revealed recurring descriptions of a phenomenon they couldn't explain: tanks that jumped. Vehicles that took hits and exploded but didn't burn. Crews who evacuated from tanks that should have killed them but somehow didn't. The consistency of these reports, across different units, different theaters, different time periods, suggested something real rather than combat confusion or wishful thinking. Dr. Paul Kennedy, an Army Ordnance engineer assigned to analyze tank loss patterns in 1946, examined 127 Sherman hulks recovered from European battlefields. His classified report, declassified in 1982, identified 17 cases where belly armor failure appeared to have vented internal explosions away from crew compartments. Kennedy noted, "The M4's thin ventral armor, intended as a weight-saving measure, inadvertently provided a pressure relief path during certain types of internal combustion events. This was not by design and should not be considered a safety feature, but statistical analysis suggests crew survival rates in these specific incidents exceeded baseline expectations for penetrated vehicles. Kennedy's report recommended against publicizing the findings. The reasoning was cynical but practical, acknowledging that thin belly armor sometimes saved crews might lead to operational assumptions that endangered tankers. Better to reinforce existing doctrine, avoid penetration, maintain standoff distance, use terrain for protection, than suggest the Sherman had any built-in survival advantages. But the tankers knew. In the oral histories collected from Sherman veterans over subsequent decades, the pattern emerged. Tanks that exploded but didn't burn. Crews who survived impacts that should have killed them, but somehow didn't. Men who climbed out of shattered Shermans wondering why they were alive when so many others had burned. Sergeant Michael Whitman's crew returned to combat in August 1944 in a new Sherman. They fought through France, into Germany, and ended the war near the Elbe River. They survived, though their second Sherman was destroyed by a Panzerfaust in October 1944, and their third threw a track in January 1945 and was abandoned during a retreat. 3 Shermans, all losses, all survived. Luck, certainly. Skill, probably. But Whitman never forgot July 18th and the tank that exploded instead of burning. The Sherman's fire vulnerability continued throughout the war, despite modifications. The 76mm gun variants introduced in late 1944 had better anti-tank performance but retained gasoline engines and similar fire rates when penetrated. The British, desperate to improve survivability, developed the Sherman Firefly with a 17-pounder gun that could match German armor at range. But Firefly still burned like standard Shermans because the gun was the only modification. American tanker doctrine evolved to work around the Sherman's weaknesses. Tank destroyers, fast, heavily armed vehicles with open-topped turrets, engaged enemy armor, while Shermans provided support and engaged soft targets. When Shermans had to fight enemy tanks, they used numerical superiority. 4 or 5 Shermans attacking one Tiger or Panther from multiple angles, accepting losses to achieve kills. The mathematics worked. Sherman production vastly exceeded German tank production, but individual crews paid the price. By 1945, the ratio of Shermans to German tanks in most engagements was 5-to-1 or higher. American tactical doctrine accepted that 2 or 3 Shermans would be lost, destroying one German tank. This exchange rate was sustainable because replacement Shermans arrived continuously while German tank production had collapsed under Allied bombing. The Sherman won through attrition, not through technical superiority. But the human cost was real. Each destroyed Sherman averaged 1.8 crew casualties, killed or seriously wounded. Multiply that by 2,041 destroyed Shermans in Northwest Europe alone, and the total approaches 3,700 casualties. Add Mediterranean, Pacific, and other theaters, and Sherman fire vulnerability killed or wounded approximately 6,000 to 8,000 American tankers during the war. Could this have been prevented? Partially. The British developed diesel-powered Shermans using Caterpillar engines, the Sherman II, which had significantly lower fire rates when penetrated. These variants were available from 1943 but never adopted by U.S. forces due to logistics concerns about maintaining separate fuel supply chains. American Shermans continued using gasoline engines until the M26 Pershing appeared in February 1945, too late to affect the war's outcome. The decision to continue gasoline-powered Sherman production was pragmatic. Maintaining production rates was more important than improving individual tank survivability. The Army needed 50,000 tanks, more than it needed perfectly designed tanks. This calculus was probably correct from a strategic perspective. Numerical superiority won battles, but it meant individual tankers fought in vehicles they knew could kill them, through design flaws rather than enemy action. The belly armor phenomenon, The explosive venting that occasionally saved crews was never officially acknowledged during the war. It couldn't be. Admitting that crew survival sometimes depended on the tank exploding would have shattered morale. Better to maintain the fiction that the Sherman was adequately protected and that crew survival depended on skill and tactical employment rather than random chance and design flaws. But the crews knew the truth. They knew the Sherman burned. They knew German tanks could kill them from ranges where they couldn't effectively fight back. They knew their survival often depended on factors beyond their control: where the shell hit, whether fuel vapor had accumulated, whether the explosion vented down instead of up. And they kept fighting, because the alternative was losing the war. The psychological burden of fighting in Sherman tanks was substantial. Post-war psychiatric studies of armored veterans showed significantly higher rates of combat fatigue and trauma among Sherman crews compared to infantry or artillery. The knowledge that their vehicle could become a death trap, that penetration meant a coin flip between evacuation and burning, created chronic stress that cumulative combat exposure intensified. Technical Sergeant Robert Early, a Sherman commander who survived 4 tanks destroyed in combat, described the experience in a 1947 interview. "Every time you buttoned up, you wondered if this was the time. Would this be the mission where you took the hit that didn't explode out the bottom, where the fire came before you could bail? You'd see other tanks brew up, and you'd think, that's me tomorrow, that's me next week. Eventually, you just accepted it. Either you'd survive or you wouldn't, and worrying didn't change anything." This fatalism was common among Sherman crews. They couldn't control the fundamental design of their vehicle. They couldn't make it less flammable or better armored. They could only control tactics: hull-down positions, flanking maneuvers, immediate evacuation when hit. Everything else was chance. The Sherman's defenders, then and now, point out that it was never intended to fight enemy tanks primarily. American doctrine designated tank destroyers for anti-armor work. Shermans were supposed to exploit breakthroughs, support infantry, and engage soft targets. Against these missions, the Sherman performed adequately. Its reliability was excellent. Its production numbers were overwhelming. Its logistical footprint was manageable. But doctrine collapsed when contact was made. German tanks appeared where they weren't supposed to. Tank destroyers weren't always available. Sherman crews found themselves in point-blank duels with Panthers and Tigers, fighting with vehicles whose design assumed they'd never face heavy armor. The Sherman's 75 mm gun couldn't reliably penetrate German heavy tanks frontally. Its armor couldn't protect against German anti-tank guns, and its gasoline engine turned every penetration into a potential funeral pyre. Yet, the Sherman achieved its strategic purpose. It was available in overwhelming numbers when needed, it could be shipped across oceans, it could be repaired in field conditions, it could be operated by crews with minimal training. These factors mattered more than individual technical excellence in a war where material superiority determined outcomes. The final accounting showed 49,234 M4 Shermans produced during World War II. Of these, approximately 8,000 were destroyed in combat across all theaters. The survival rate, about 84%, looked respectable until examining crew casualties. Those 8,000 destroyed tanks represented approximately 14,000 to 16,000 crew casualties killed or seriously wounded. The Sherman's design contributed significantly to this toll through fire vulnerability that better engineering could have reduced. But consider the alternative. If production had been delayed 6 months to redesign the Sherman with diesel engines and better armor, those 6 months of missing tanks might have cost far more lives in prolonged campaigns, failed offensives, and infantry without armored support. the Army chose to field adequate tanks immediately rather than superior tanks eventually. This decision killed thousands of tankers, but probably saved tens of thousands of infantry and shortened the war. The ethical calculation is uncomfortable, but unavoidable. The Sherman's flaws were known, the fire vulnerability was documented, the casualties were predicted, and production continued because winning the war required accepting these costs. American tankers fought in death traps because those death traps were available in quantities that enabled victory. The phenomenon of explosive venting, tanks that saved their crews by exploding, remained a footnote in official histories. The Army never acknowledged it publicly. Technical manuals never mentioned it, training doctrine never incorporated it. It was simply too risky to suggest that crew survival might depend on the tank experiencing a specific type of catastrophic failure. But the phenomenon was real. Post-war analysis identified dozens of cases where internal explosions vented through belly armor rather than crew compartments. These cases were statistically significant, enough to suggest a pattern rather than random chance, but not common enough to change operational doctrine. Most penetrated Shermans still burned normally. The explosive venting saved hundreds of crew members, perhaps a few thousand across all theaters, but couldn't save the thousands who died in conventional fires. In the decades after the war, Sherman veterans occasionally discussed the phenomenon at reunions and in memoirs. They described tanks that jumped, vehicles that exploded but didn't burn, moments when they should have died but didn't for reasons they couldn't explain. The descriptions were consistent: sudden explosion, pressure wave, smoke, then survival instead of fire. Dr. Kennedy's classified report remained the only official acknowledgement until the 1980s. When declassified, it provided scientific confirmation of what veterans had known. The Sherman's thin belly armor occasionally vented explosions away from crews. The report also noted that this was entirely accidental, an unintended consequence of weight-saving measures, and should never be considered a design feature. The Sherman that saved its crew by exploding became a metaphor for American armor doctrine in World War II. Flawed by design, adequate in execution, successful through numbers. The tank had problems that better engineering could have solved, but solving those problems would have delayed production, and production delay would have cost more lives than the flaws killed. By 1947, the Sherman was obsolete. The M26 Pershing, M46 Patton, and eventually M48 and M60 tanks replaced it with designs that incorporated lessons from Sherman casualties: thicker armor, more powerful guns, and diesel engines that burned less readily when penetrated. The post-war tanks were what the Sherman should have been: purpose-built combat vehicles rather than improvised solutions to immediate needs. But those improved tanks couldn't have been mass-produced in 1942, 1943 with existing industrial capacity. They required technologies and manufacturing capabilities that didn't exist yet. The Sherman was what America could build when it needed tanks immediately. It was adequate rather than excellent, but adequacy in quantity defeated excellence in scarcity. The final statistics tell the story. German armor, technically superior in most measures, lost the war because there were never enough Tigers, Panthers, or tank destroyers to match American and Soviet numbers. Germany produced approximately 30,000 tanks and tank destroyers during the war. America produced 88,000 tanks plus 67,000 other armored fighting vehicles. The Soviet Union produced 100,000 tanks. Axis forces faced a 6-to-1 disadvantage in armored vehicles by 1944. Technical superiority didn't compensate for numerical inferiority. German tankers fought in vehicles that could kill multiple Shermans but eventually died when the 5th or 6th Sherman maneuvered to a flanking position. The mathematics of attrition favored mass production over engineering excellence. The Sherman's flaws were real but irrelevant to strategic outcomes because they were fielded in overwhelming numbers. But for individual crews, the Sherman's flaws were everything. Whether they survived depended on those flaws, whether the penetrating shell hit ammunition or fuel, whether the fire suppression system worked, whether accumulated vapor exploded instead of burned, whether the explosion vented down instead of up. These random factors determined life and death more reliably than skill or courage. Sergeant Michael Vittman survived the war and returned to Ohio. He never spoke publicly about his experience until 1985, when a local historian interviewed Sherman veterans. His description of July 18, 1944, the tank that exploded but didn't burn, was matter of fact. "We got hit, Sherman blew up, we got out. Tank was wrecked, but we were alive. Happened to other crews too, from what I heard. Couldn't explain it then. Still can't really. Just lucky, I guess." The word was luck. Luck that the shell hit where it did. Luck that the explosion vented down. Luck that hatches weren't jammed. Luck that the crew reacted fast enough. Luck multiplied by chance, multiplied by random factors that couldn't be controlled or predicted. The Sherman that saved its crew by exploding did so through accident, not design. In 1994, at a Sherman Veterans reunion in Fort Knox, survivors discussed the phenomenon openly for the first time. Over 200 former tankers attended. When asked how many had experienced or witnessed explosive venting, tanks that jumped but didn't burn, approximately 40 raised their hands, 20%, a significant fraction, though still a minority of Sherman casualties. These survivors shared a common experience: being alive when they shouldn't be for reasons they couldn't fully explain. Their tanks had been destroyed. Their vehicles had exploded, but they'd survived when thousands of their comrades hadn't, because random chance and an unintended design feature had vented deadly pressure away from them instead of through them. The Army never apologized for the Sherman's flaws. There was nothing to apologize for. The tank was fit for purpose within the constraints of 1940s technology and industrial capacity. It kept armies mobile, defeated Axis armor through numerical superiority, and achieved every strategic objective assigned to it. That it killed thousands of its own crews through design-related fire vulnerability was tragic, but wasn't negligence. It was the cost of fielding adequate vehicles immediately, rather than perfect vehicles eventually. The Sherman's legacy is complex. It was simultaneously the weapon that won armored warfare in Northwest Europe and the death trap that burned American tankers who couldn't evacuate fast enough. It was the most produced Allied tank because it could be manufactured in massive quantities, and it needed those quantities because its individual capabilities were modest compared to German armor. It succeeded strategically while failing many of its crews individually. And occasionally, through a design flaw that shouldn't have existed, it saved crews by exploding. The thin belly armor that was supposed to save weight inadvertently provided a pressure relief path that vented internal explosions downward. This wasn't protection. It wasn't a safety feature. It was an accident of engineering that happened to align favorably for a few hundred crews out of the thousands who fought in Shermans. The tank that saved its crew by exploding represents everything contradictory about American armor in World War II. Flawed by design, but adequate in practice. Vulnerable individually, but overwhelming collectively. Capable of burning crews alive, or accidentally saving them through the same design features. The Sherman was never the tank American tankers wanted, but it was the tank they had, and they used it to win the war despite its flaws. By May 1945, Sherman crews had destroyed Axis armor from North Africa to Germany, from Italy to the Philippines. They'd fought in vehicles they knew could kill them through design flaws. They'd watched comrades burn in brewing up Shermans. They'd climbed into new tanks after their previous ones were destroyed. And some, a few hundred out of thousands, had survived because their tank exploded in exactly the right way, venting pressure through weak armor instead of through the crew compartment. The final numbers: 49,234 Shermans built, 8,000 destroyed in combat, 14,000 to 16,000 crew casualties, and approximately 300 to 500 crews saved by explosive venting, a phenomenon that shouldn't have existed but did, that shouldn't have worked but sometimes did, that was simultaneously a design flaw and a miracle. The Sherman that saved its crew by exploding wasn't the exception that proved the rule. It was the reminder that war creates chaos. Chaos creates random outcomes, and sometimes random outcomes align favorably despite the design. The crews who survived explosive venting were lucky, not protected. Their tanks failed catastrophically. They just failed in a direction that didn't kill them. At the National Armor and Cavalry Museum at Fort Benning, a cutaway Sherman displays the interior layout that became so familiar to thousands of American tankers: the fuel tanks, the ammunition storage, the crew positions, the thin belly armor. Visitors see the mechanical details that determined whether crews lived or died when German shells penetrated. The placard describes the Sherman's service history, production numbers, and combat record. It doesn't mention the fire vulnerability that killed thousands. It doesn't discuss the explosive venting that saved hundreds. It presents the Sherman as American tank historians generally do, as an adequate vehicle that succeeded through numerical superiority despite technical shortcomings. But for the crews who fought in Shermans, the technical shortcomings were existential threats. Every mission was a reminder that their vehicle's design might kill them before the enemy could. Every penetration was a moment of chance: fire or explosion, death or survival, burning or venting. They couldn't control which outcome occurred. They could only react when it did. The Sherman that saved its crew by exploding became a story passed among veterans, a reminder that survival sometimes depended on factors beyond control. The tank that should have burned, but exploded instead. The crew that should have died, but walked away. The design flaw that became a miracle through random chance and mechanical failure. They climbed into Shermans knowing the risks. They fought in vehicles that could become death traps, and occasionally, through accidents of engineering and chance, they survived when everything suggested they shouldn't have. The Sherman's greatest flaw saved a few while killing thousands. Not justice, not fairness, just chaos and statistics and random outcomes in a war where survival often depended on which way pressure vented when armor failed. The tank that saved its crew by exploding did so by accident, not by design. But for those crews, Sergeant Whitman's among them, the distinction didn't matter. They were alive when they should have been dead. Their Sherman had failed catastrophically, and that failure, through mechanical chance, had vented away from them instead of through them. Adequate tanks in overwhelming numbers won the war. Thousands of crews died in those adequate tanks. Hundreds survived through accidents of design. And the Sherman remained what it had always been: good enough to win, flawed enough to kill, and occasionally lucky enough to save those it should have destroyed. The explosion that saved them shouldn't have worked, but it did, and they survived to remember the tank that killed itself to spare its crew. The phenomenon became known informally among ordnance personnel as bottoming out events or simply blowouts. The term never appeared in official documentation because acknowledging it would require explaining why American tanks had vulnerable belly armor and volatile fuel systems. But in maintenance depots and recovery units, the pattern was recognized: Shermans that jumped, crews that survived, belly armor blown out while the crew compartment remained relatively intact. Captain Harold Russell, a maintenance officer with the 3rd Armored Division, kept unofficial notes on tank losses throughout the European campaign. His records, donated to the Army Heritage Center in 1978, documented 47 cases between June 1944 and April 1945 where Shermans experienced catastrophic belly armor failure with crew survival rates exceeding 80%. Russell noted, "These tanks took hits that should have brewed them up. Instead, they experienced what crews described as a violent upward jolt followed by smoke, but no fire." On inspection, belly plates were found separated from welds or bent outward. Internal damage was severe, but crews evacuated with injuries consistent with blast overpressure rather than burns. Russell's notes also documented the pattern's prerequisites. The explosion had to occur before ammunition storage was compromised. Fuel vapor concentration had to reach explosive rather than merely flammable levels. The ignition had to be rapid enough to create pressure rather than sustained burning, and the belly armor had to fail before the explosion found other exit paths. These conditions aligned infrequently, which explained why blowouts saved hundreds rather than thousands. The engineering explanation emerged years later when metallurgists examined preserved Sherman hulks. The belly armor welds were the weakest structural points in the lower hull, not by design intent, but because bottom plates were among the last components assembled. Welding standards for belly armor were less stringent than frontal or side armor, because threats from below, primarily mines, were considered less likely than threats from the horizontal plane. When internal pressure from gasoline vapor explosion exceeded approximately 50 psi, the threshold varied by welding quality and armor thickness, the belly plates separated at the welds. The explosion path followed the line of least resistance, downward through relatively thin armor with relatively weak welds, rather than upward through thicker armor with stronger structural integrity. The result was dramatic but directional. The pressure vented away from the crew rather than through them. This explanation was mechanically sound but strategically embarrassing. It confirmed that the Sherman's survivability sometimes depended on structural weaknesses rather than design strengths. American armor doctrine emphasized protection through frontal armor thickness and angled surfaces. Acknowledging that crews occasionally survived because the bottom fell out of their tank contradicted the narrative of engineered protection. So the phenomenon remained unacknowledged officially. Crews who experienced it understood they'd been lucky. Maintenance personnel who inspected the hulks recognized the pattern but didn't report it up the chain, and ordnance engineers who analyzed loss statistics saw the anomaly but classified their findings. The Sherman that saved its crew by exploding became an open secret, known to those who needed to know, hidden from those who might question why the tank had such weaknesses in the first place. The alternative, redesigning the Sherman to eliminate fire vulnerability, was examined multiple times during the war. Each examination reached the same conclusion. Fundamental changes would interrupt production for 6 to 12 months. The redesigned Sherman might save crew lives, but would cost strategic advantage by reducing available armor during the redesign period. The military chose continuous production of flawed tanks over interrupted production of improved tanks. This decision was defensible in strategic terms. By mid-1944, the Allies had achieved material superiority in virtually every category: armor, artillery, aircraft, logistics. American production exceeded German capacity by factors of 3 to 10, depending on the system. Interrupting Sherman production would squander this advantage for marginal improvements in individual tank survivability. Better to maintain the flow of adequate tanks than risk strategic pause for tactical improvements. But the decision had human cost that statistics couldn't fully capture. Sergeant William Marsh, commander of a Sherman in the 4th Armored Division, survived 3 destroyed tanks between August and December 1944. His 3rd tank, hit by a Panzerfaust in the Ardennes, experienced a blowout that saved his crew. His letter home, archived at the National World War II Museum, captured the psychological burden. "We were in our 3rd Sherman since France. The first 2 burned. We lost men both times. The 3rd one got hit and exploded instead of burning. We got out alive, but I keep thinking about the crews in the first 2 tanks. Why did they burn when this one blew? Why them and not us? There's no answer, just chance. And that makes it worse somehow, knowing it's random." Survivor's guilt was common among Sherman crews who experienced blowouts. They'd witnessed comrades burn and brewing up tanks. They'd seen the standard pattern: penetration, fire, desperate evacuation attempts, casualties. When their own tank exploded but didn't burn, when they survived relatively intact, the randomness of it created psychological burdens that combat stress alone didn't explain. Why had they been lucky when others hadn't? There was no answer, except chance. The randomness extended beyond individual crews to entire units. The 2nd Armored Division, fighting in Northwest Europe from June 1944 through May 1945, lost 232 Shermans, destroyed by enemy action. Of these, approximately 147 caught fire in conventional patterns. 23 experienced blowouts with crew survival. 62 were destroyed by other means: ammunition explosion, catastrophic mechanical failure, or abandonment. The blowout rate was roughly 10% of destroyed tanks, significant but not dominant. But within that 10%, crew survival rates were dramatically better. Conventional fires resulted in average crew casualties of 2.3 per tank, nearly half the 5-man crew. Blowouts averaged 0.8 casualties per tank, primarily from initial penetration and blast effects rather than fire. The difference was stark: brewing up killed half the crew, blowouts killed less than 1/5. For crews who experienced blowouts, the Sherman's flaw had become their salvation. This created a perverse dynamic. Tankers feared penetration because it usually meant fire, and fire meant casualties. But some tankers who'd experienced or heard about blowouts developed a fatalistic hope: if we get hit, maybe it'll blow out instead of burning. This wasn't rational. The prerequisites for blowouts were too specific to be predictable, but combat stress doesn't respect rationality. Crews rasped at any explanation for why they might survive. Technical Sergeant Frank Novak, a Sherman gunner who survived a blowout in October 1944, described this mindset in a 1989 interview. "After it happened to us, after we got hit and the tank blew out instead of burning, word spread through the company. Guys started talking about it like it was something you could count on. Like if you got hit in the right spot, maybe you'd blow out instead of brew up. The officers tried to shut down that talk. They said it was random, not something you could rely on. But you'd hear crews saying, if we take a hit, maybe we'll get lucky like Novak's crew. It was stupid. You couldn't control it, but it gave guys something to hope for besides just burning. This hope was dangerous from a command perspective. If crews believed they might survive penetration through blowouts, they might take unnecessary risks. Tactical doctrine emphasized avoiding penetration entirely through proper positioning and engagement ranges. Crews who thought they might survive hits anyway could become careless. So company commanders and battalion officers actively discouraged discussion of blowouts, framing them as flukes rather than patterns. But the pattern existed. By war's end, documented blowouts across all U.S. armored units in Europe numbered approximately 180 to 240 cases where crews survived internal explosions that vented through belly armor. This was small compared to the thousands of conventional Sherman fires, but significant enough to represent a real phenomenon. The Sherman's flaw saved roughly one crew per armored battalion, on average, through random mechanical failure that aligned favorably. The German tankers who encountered Sherman blowouts were baffled. Hauptmann Klaus Becker, a Panther commander who engaged Shermans throughout 1944-1945, described one incident in post-war interrogation. "We hit a Sherman at approximately 700 meters. Direct hit, frontal penetration. The tank actually lifted off the ground, and smoke poured out. We expected the usual fire. Nothing, just smoke. The crew bailed out and escaped. We examined the wreck later. The bottom was blown out completely. We couldn't understand what had caused it. The penetration was frontal, the explosion was ventral. It made no sense from an engineering perspective." German after-action reports occasionally mentioned American tanks that exploded without burning or experienced unusual blast patterns, but German intelligence never identified blowouts as a systematic phenomenon because they weren't systematic. They were random events that occurred under specific conditions German observers couldn't predict or reproduce. From the German perspective, some Shermans behaved abnormally when hit. No pattern was apparent. This randomness prevented tactical exploitation by either side. Americans couldn't deliberately create blowouts. The conditions were too specific and the process was too random. Germans couldn't prevent them. They occurred after penetration, when the engagement was already decided. Blowouts were simply a chaotic element in armored combat, favoring crew survival in a small percentage of cases without altering tactical outcomes. The Sherman's fire vulnerability continued dominating crew casualties throughout the war. For every crew saved by a blowout, 10 crews died in conventional fires. The improvement represented by wet stowage and fire suppression systems reduced but didn't eliminate the problem. Shermans with all available fire protection modifications still burned in 30 to 40% of penetrations, better than the 60 to 80% of early models, but still high compared to diesel-powered tanks. By early 1945, some American units received M26 Pershing heavy tanks with 90mm guns and improved armor. The Pershing addressed Sherman deficiencies through better firepower, protection, and, critically, a more fire-resistant design. But only 200 Pershings reached Europe before VE Day, too few to replace the thousands of Shermans still in service. Most American tankers finished the war in the same vehicle they'd started with, the gasoline-powered, thinly armored Sherman. The final months of the war saw Sherman losses decline not because the tank improved, but because German resistance collapsed. By March 1945, German armor was scarce. Fuel shortages limited operations, experienced crews were dead or captured. American Shermans faced less opposition and consequently suffered fewer losses. The tank's vulnerabilities remained, but mattered less as the strategic situation evolved in America's favor. VE Day, May 8, 1945, ended combat operations in Europe. Surviving Sherman crews rotated home or prepared for redeployment to the Pacific. The tanks that had carried them through Europe were inspected, repaired if salvageable, or scrapped if too damaged. Among the hulks sent to salvage yards were dozens with blown-out belly armor, the physical evidence of blowouts that had saved their crews. These hulks were scrapped without special recognition. There were no plaques commemorating tanks that saved crews by exploding. The phenomenon remained unacknowledged, an embarrassing reminder that American armor sometimes succeeded through failure rather than design. The Sherman's official legacy emphasized its mass production, reliability, and strategic success. The fire vulnerability and occasional explosive venting were footnotes at best. But for the veterans, the experience remained vivid. At post-war reunions, Sherman crews shared stories of blowouts alongside other combat memories. The phenomenon became part of informal Sherman lore, the tank that could kill you by burning or save you by exploding, depending on random factors nobody controlled. The lucky lottery, where lucky crews survived and unlucky crews burned. The statistical analysis of Sherman operations, conducted by Army Ordnance in 1946 to 1947, quantified the phenomenon without publicizing it. The classified report identified 214 documented blowout events in Northwest Europe, with crew survival rates of 78% compared to 42% for conventional fires. The report concluded, explosive venting through ventral armor failure represents an unintended consequence of the M4 structural design. While this phenomenon enhanced crew survival in specific cases, it should not influence future armor development as it derives from weaknesses rather than strengths. Future designs should eliminate fire vulnerability entirely rather than rely on random pressure venting. This conclusion shaped post-war American tank development. The M46, M47, M48, and M60 tanks all used diesel engines, reducing fire vulnerability significantly. The M1 Abrams, introduced in 1980, used a gas turbine running on jet fuel with fire characteristics closer to diesel than gasoline. American armor designers spent 4 decades eliminating the problems that had killed Sherman crews, learning lessons paid for in blood during World War II. But those lessons came too late for the 6,000, 8,000 American tankers killed or seriously wounded in Sherman fires. The Sherman that saved its crew by exploding was the exception that proved the rule. The tank's design was fundamentally flawed, crew survival often depended on chance, and American tankers won armored warfare despite, rather than because, of their vehicle's characteristics. The human stories behind the statistics remained. Private First Class David Kim, loader in Sergeant Whitman's crew, survived the July 18th blowout but was killed 2 months later when his new Sherman took a direct hit from an 88mm gun that penetrated the turret. The blast killed him instantly, a different random outcome in the mechanical lottery of armored combat. His death, like his survival 2 months earlier, was determined by factors beyond his control. Where the shell hit, how the tank failed, whether the explosion vented favorably. Sergeant Whitman carried Kim's death for the rest of his life. In his 1985 interview, he said, "Kim survived when we should have all died. Then he died when maybe he should have survived. There's no logic to it, no reason. Just random chance in a metal box that could kill you a dozen different ways. We survived the blowout together. He didn't survive the next hit. That's war. That's what the Sherman was. A dice roll every time you buttoned up." This fatalism characterized many Sherman veterans. They'd survived random outcomes while comrades hadn't. They'd experienced the full spectrum of Sherman failures: fires, blowouts, ammunition explosions, mechanical breakdowns. They'd learned that survival depended partly on skill and mostly on chance. The Sherman that saved its crew by exploding was just one example of how chaos and mechanics intersected in ways that couldn't be predicted or controlled. By the 1990s, most Sherman veterans had passed. The few remaining survivors were in their 70s and 80s, memories fading but certain experiences remaining vivid. The blowouts, the fires, the moments when chance determined life or death. At final reunions, elderly tankers would discuss what happened to them 60 years earlier in French hedgerows and German forests, trying to make sense of survival that still felt random decades later. The last major Sherman veteran reunion occurred in 1994 at Fort Knox. Approximately 150 veterans attended. When the moderator asked how many had experienced or witnessed a blowout, 32 raised their hands, 20%, consistent with the wartime documentation. These men survived because their tanks exploded in a specific way that vented pressure downward. They were alive because of a design flaw that occasionally worked as an unintended safety feature. One veteran who requested anonymity summarized the experience. "The Sherman was a death trap that sometimes became a life raft. It could burn you alive or blow out and save you. You never knew which until it happened. You learned to accept that. You climbed in every day knowing it might be the last time. And if you were lucky, really lucky, maybe the tank would fail in a way that didn't kill you. That's what the blowout was, lucky failure. The Sherman saving you by destroying itself in exactly the right direction." This description captured the essential truth about the Sherman's explosive venting phenomenon. It wasn't protection, it wasn't a safety feature, it was favorable failure, catastrophic mechanical breakdown that happened to direct deadly energy away from the crew rather than through them. The tank was still destroyed, the mission was still failed, but the crew survived, which in the context of Sherman operations was the most anyone could hope for when armor was penetrated. The final accounting of Sherman blowouts will never be complete. Many cases went undocumented in the chaos of combat. Some were misidentified as conventional fires. Others weren't recognized as blowouts by crews who evacuated too quickly to observe what happened. The 214 documented cases in Europe represent a minimum, with the actual total possibly reaching 300–400 across all theaters. But even at the upper estimate, blowout saved perhaps 2,000 crew members out of the 6,000–8,000 killed or seriously wounded in Sherman fires. A significant number, but a minority. Most Sherman fires followed conventional patterns: penetration, ignition, spreading flames, desperate evacuation attempts, casualties. The blowout was the exception, the random favorable outcome in a system designed to kill its occupants when armor failed. The Sherman that saved its crew by exploding represented everything contradictory about American armor in World War II compressed into a single phenomenon. The tank's greatest weakness, volatile fuel in a thinly armored hull, occasionally became a survival mechanism through unintended structural failure. The design flaw that killed thousands sometimes saved individuals through random mechanical breakdown that vented favorably. This contradiction never resolved. The Sherman remained what it had always been: adequate enough to win, flawed enough to kill, and occasionally lucky enough to save through the same weaknesses that made it deadly. American tankers fought in these vehicles, died in these vehicles, and sometimes survived these vehicles through accidents of engineering that shouldn't have worked, but did. At the National Infantry Museum at Fort Benning, the preserved Sherman on display shows no external evidence of the blowout phenomenon. The belly armor is intact, restored to factory condition. Visitors see a clean, maintained example of American armor engineering. They don't see the blown-out floor plates, separated welds, and buckled armor that characterized blowout survivors. The messy reality of combat is sanitized into museum condition, but the reality remains in veteran testimonies, maintenance records, and classified ordnance reports. The Sherman that saved its crew by exploding did so by accident. But for those crews, the accident meant survival. The design flaw meant life, and the random failure meant they walked away from battles that should have killed them, carrying memories of the tank that destroyed itself in exactly the right way at exactly the right moment. Adequate tanks built in overwhelming numbers won the war. Thousands died in those tanks. Hundreds survived through accidents of design, and the Sherman remained what it always was: good enough to win, deadly enough to fear, and occasionally miraculous enough to save through the same flaws that made it lethal. The explosion that saved them was never supposed to work, but it did, and they survived to tell the story of the tank that sacrificed itself to spare its crew. The phenomenon extended beyond individual survival stories into the broader calculus of American armor doctrine. By late 1944, Army ordnance had accumulated enough field reports to recognize that blowouts, while rare, occurred with sufficient frequency to warrant technical investigation. A team of engineers was dispatched to forward maintenance areas in December 1944 to examine hulks and interview survivors. Lieutenant Colonel Bernard Watkins led the investigation. His team examined 37 Sherman hulks that had experienced apparent blowout events across units of the 1st and 3rd Armies. The pattern was consistent: penetration to forward or mid-hull, fuel system compromise, rapid pressure buildup, ventral armor failure. In 29 of 37 cases, the crew had survived with injuries but no fatalities. In conventional Sherman fires examined for comparison, crew fatality rates exceeded 50%. Watkins' preliminary report, filed in January 1945, noted, "The survival differential between explosive venting events and conventional post-penetration fires is statistically significant. However, the mechanism relies on structural failure of the weakest hull components, specifically the ventral armor welds. Recommending this as a survival feature would require acknowledging fundamental design weaknesses. Further, the conditions necessary for favorable venting cannot be reliably reproduced. This phenomenon should be documented for post-war analysis but not incorporated into operational doctrine or crew training." The recommendation to avoid operational acknowledgement was accepted immediately. Crew training manuals continued emphasizing immediate evacuation when penetrated, with no mention of blowout possibilities. Tactical doctrine continued stressing penetration avoidance through proper positioning. Official casualty reports documented Sherman fire deaths without distinguishing between conventional fires and blowout survivors. The phenomenon remained classified at the field investigation level. But suppressing official acknowledgement didn't prevent crews from discussing it. By early 1945, blowout stories circulated widely among armored units. Crews who'd experienced them shared their stories. Maintenance personnel who'd inspected the hulks described the characteristic damage patterns. Tank commanders briefed their crews on what to do if the tank jumped, the common description, rather than burned normally. This informal knowledge transmission created an interesting dynamic. Officially, blowouts didn't exist. Unofficially, every armored battalion knew about them. Crews couldn't predict them, couldn't cause them, couldn't rely on them. But they knew the possibility existed, and that knowledge provided psychological comfort, however irrational. Maybe, if we get hit, we'll be lucky like those other crews. Maybe the tank will blow out instead of burning. Staff Sergeant Raymond Cooper, a platoon sergeant in the 9th Armored Division, described this mentality in a 1987 oral history. By February 45, everybody had heard stories about tanks that blew out. Guys talked about it like it was something that might save you if you got hit. The smart ones knew it was mostly bullshit. You couldn't count on it happening, but it was better than nothing. Better than just accepting that a penetration meant you'd probably burn. Even a small chance of surviving differently gave guys something to hang on to. This psychological effect may have been the blowout phenomenon's most significant impact. Not the hundreds of lives saved directly, but the thousands of crews who fought with slightly less fatalism because they knew random chance might favor them. Whether this improved combat effectiveness or increased risk-taking behavior was impossible to determine, but it affected morale in ways that pure statistics couldn't measure. The final months of the war saw Sherman losses decline dramatically as German resistance collapsed. By April 1945, American armor faced minimal opposition. The few remaining German tanks were immobilized by fuel shortages. Anti-tank gun crews lacked ammunition. Panzerfaust teams were killed or captured before they could engage. Sherman vulnerability mattered less because threats had largely evaporated. But in isolated engagements, the pattern continued. On April 9, 1945, near Göttingen, Germany, a Sherman from the 3rd Armored Division took a Panzerfaust hit to the right hull side. The shaped charge penetrated, ignited fuel vapor, and the resulting explosion vented through belly armor. The crew evacuated with minor injuries. It was one of the last documented blowouts of the European War, a phenomenon that had saved hundreds, occurring once more in the conflict's final days. VE Day ended combat operations, but didn't end analysis of Sherman performance. Throughout 1945-1946, Army Ordnance conducted comprehensive reviews of every aspect of American armor operations. The Sherman fire vulnerability received extensive attention. Thousands of after-action reports were compiled. Hundreds of crew interviews were conducted. Dozens of hulks were shipped to Aberdeen Proving Ground for detailed examination. The blowout phenomenon appeared throughout this documentation as an acknowledged but unexplained anomaly. Engineers recognized that some Shermans vented explosions through belly armor with enhanced crew survival. They documented the mechanical process, rapid pressure buildup exceeding weld strength, directional venting through the path of least resistance. But they couldn't explain why some fuel vapor explosions created this outcome, while most created conventional fires. Dr. Robert Heinlein, not the science fiction author, but an Army Ordnance metallurgist, led the technical analysis in 1946. His team conducted pressure testing on preserved Sherman hulls, introducing measured explosive charges into sealed crew compartments to observe failure modes. The results were enlightening and disturbing. Heinlein's tests showed that belly armor consistently failed before upper hull structure when internal pressure exceeded 45 to 55 psi. This confirmed that ventral venting was the path of least resistance. However, achieving rapid pressure buildup required very specific conditions. Fuel vapor concentration between 1.4 and 7.6% by volume, ignition source providing rapid rather than progressive combustion, and timing that preceded ammunition or hydraulic fluid involvement. These conditions occurred randomly based on factors crews couldn't control: how long the engine had been running, ambient temperature, ventilation patterns inside the hull, and precise location of the penetrating shell. Heinlein's report concluded, explosive venting through ventral armor represents a survival mechanism that activates under conditions too specific to be tactically useful. The phenomenon cannot be reliably induced and should not inform future design. However, crew survival rates in documented venting events exceed baseline fire survival by approximately 40 percentage points, representing significant life-saving potential in cases where conditions align favorably. The report was classified secret and remained so until 1983. Its findings influenced post-war American tank design primarily through negative lessons: eliminate volatile fuel, strengthen hull integrity uniformly rather than relying on weak points for pressure relief, design fire suppression systems that prevent explosive vapor accumulation. The M46, M47, and subsequent tanks incorporated these lessons, eliminating the conditions that made Sherman blowouts possible. But eliminating the conditions also eliminated the occasional life-saving outcome. Post-war American tanks didn't experience blowouts because they didn't use gasoline, didn't have weak belly armor, and didn't allow vapor accumulation. This was unambiguously positive. Fire casualties dropped dramatically in subsequent conflicts, but it also meant that the random survival mechanism that had saved hundreds of Sherman crews disappeared from American armor. The Korean War, beginning in June 1950, deployed Shermans alongside newer M46 Pattons and M4A3E8 Easy 8 variants. These Shermans retained gasoline engines and similar fire vulnerability to World War II models. Blowout events occurred occasionally: 3 documented cases in U.S. Army records, 2 in Marine Corps operations. The phenomenon persisted wherever gasoline-powered Shermans fought, following the same random patterns as in World War II. But Sherman use in Korea was limited compared to World War II. Newer tanks gradually replaced them. By 1953, most American armor was diesel-powered, eliminating the gasoline vapor accumulation that enabled blowouts. The phenomenon became historical rather than operational, a characteristic of obsolete vehicles being phased out of service. Foreign militaries using surplus Shermans experienced blowouts into the 1960s and 1970s. Israeli Shermans in 1956 and 1967, Pakistani Shermans in 1965, and various other operators reported occasional instances of tanks that exploded without burning after penetration. But documentation was sparse, and most militaries didn't investigate the phenomenon systematically. The blowout remained what it had always been: a random occurrence that saved crews occasionally without being reliable enough to depend on. The last combat use of Shermans occurred in the 1970s in various regional conflicts. By then, the tank was hopelessly obsolete. Its armor couldn't withstand modern anti-tank weapons, its gun couldn't penetrate modern armor, and its gasoline engine was a liability that every other nation had eliminated decades earlier. The final Shermans were destroyed, scrapped, or relegated to static displays, ending 70 years of service across dozens of militaries. With them ended the blowout phenomenon. Modern tanks don't experience explosive venting through belly armor because they're not designed in ways that allow it. They use diesel or turbine engines that don't produce explosive vapor. They have uniform hull strength that doesn't provide weak points for pressure relief. They incorporate fire suppression that prevents vapor accumulation. The engineering that eliminated Sherman vulnerabilities also eliminated the occasional miracle that came from those vulnerabilities. The historical record of Sherman blowouts remains incomplete. The 214 documented cases in Northwest Europe, plus scattered instances in other theaters and post-war conflicts, represent a minimum count. The actual total was likely 300 to 500 cases where crews survived internal explosions that vented through belly armor. Against the approximately 8,000 Sherman losses to enemy action in WW2, blowouts represented 4 to 6% of destroyed tanks. But that 4 to 6% had survival rates 40 percentage points higher than conventional fires. If 300 tanks experienced blowouts with 78% crew survival versus 42% for conventional fires, approximately 108 additional crew members survived who would have died in normal fires. If the actual number was 500 blowouts, approximately 180 additional survivors. Not thousands, but not insignificant either. Each survivor was someone who returned home because random chance and mechanical failure aligned favorably. The families of those survivors never knew how close their loved ones came to dying. The official casualty report simply noted vehicle destroyed, crew survived. No mention of explosive venting or belly armor failure or the random mechanical lottery that determined the outcome. The survivors themselves often didn't fully understand what happened. They knew the tank exploded differently than expected, knew they survived when they shouldn't have, but couldn't explain the mechanics beyond "we got lucky." And they had gotten lucky. Lucky that fuel vapor reached explosive concentration rather than merely flammable. Lucky that ignition occurred before ammunition was involved. Lucky that pressure found the weak belly armor before finding other exit paths. Lucky that welds failed at the right moment in the right direction. Lucky that the explosion vented down instead of up. A chain of mechanical chances that all had to align perfectly, and for a few hundred crews across 5 years of global warfare, they did. The Sherman veterans who survived blowouts carried unique burdens. They'd experienced the full spectrum of Sherman vulnerability: penetration, explosion, survival against odds. They knew comrades who'd burned. They'd heard the screams over radio nets as crews died in brewing tanks. They'd seen the smoke and flame that marked Sherman losses across every battlefield. And then their own tank had been hit, had exploded, and they'd survived because the explosion went the right direction. Master Sergeant James Chen, the bow gunner from Cobra who survived the July 18, 1944 blowout, was asked in 1992 how he felt about surviving. His answer captured the complexity. "Grateful, obviously, I got to come home. Got to have a family, got to live 70 more years. But there's guilt too. Why me? Why did our tank blow out when so many others burned? There's no answer, just chance. And that makes you think about all the guys who weren't as lucky, who died because their tank exploded up instead of down. You can't make sense of it. You just accept that you survived and they didn't, and there's no justice or fairness or reason to it, just chaos and chance." This inability to find meaning in random survival was common among blowout survivors. They couldn't attribute their survival to skill or courage or divine intervention. It was mechanical chance, pure and simple. The tank failed in a specific way that happened to save them. Nothing more, nothing less. For men who'd been trained to believe survival depended on tactical competence and proper procedures, this randomness was psychologically difficult to process. The broader lesson about Sherman design remained politically sensitive for decades. American military historians emphasized the Sherman's production advantages, reliability, and strategic success. They acknowledged the fire vulnerability but framed it as acceptable given wartime constraints. The blowout phenomenon, which highlighted just how severe the vulnerability was, received minimal attention in official histories. It wasn't until the 1980s, when Vietnam-era transparency standards were applied retroactively to WW2 documentation, that comprehensive information about Sherman fires and blowouts became publicly available. The declassified reports, crew testimonies, and technical analyses provided a complete picture. The Sherman had killed thousands of American tankers through design-related fire vulnerability and had occasionally saved hundreds through unintended explosive venting. The engineering that eliminated Sherman vulnerabilities also eliminated the occasional miracle that came from those vulnerabilities. Modern armor historians debate whether the Sherman's flaws were necessary compromises or preventable failures. Some argue that diesel engines were available and should have been mandated from the start. Others contend that gasoline engines enabled the mass production that won the war, and casualties were the unavoidable price of that production. The debate continues without resolution because it asks fundamentally counterfactual questions about alternative designs that weren't built. What's not debatable is the experience of the crews. They fought in Shermans. The tanks burned. The tanks occasionally exploded favorably. Men died, men survived. The Sherman was simultaneously the vehicle that won armored warfare in Northwest Europe and the death trap that burned American tankers who couldn't escape fast enough. Both descriptions are accurate. Both describe the same machine. At the U.S. Army Armor School at Fort Benning, instructors teaching the history of American armor briefly mentioned Sherman fire vulnerability and the various modifications attempted to address it. They don't mention blowouts. The phenomenon is considered too specific, too random, and too historically minor to warrant class time. Students learn that the Sherman burned, learn the casualty statistics, learn the tactical doctrine developed to mitigate vulnerability. The occasional miracle of explosive venting remains a footnote in classified reports rather than a teaching point. But for the veterans who experienced it, who survived because their tank exploded in the right direction, the phenomenon was everything. It was the difference between death and survival, between burning and breathing, between becoming a casualty statistic and coming home. The Sherman that saved its crew by exploding wasn't a footnote for them. It was their entire life, the random mechanical chance that determined every year they lived after July or August or October 1944. Sergeant Michael Whitman died in 2003 at age 84. His obituary mentioned his service in the 2nd Armored Division, his 3 Purple Hearts, his Bronze Star. It didn't mention Cobra, or the blowout, or the 5 men who survived when they shouldn't have. Those details were in his unpublished memoir, donated to the National Archives, where they remain as testimony to what happened on an obscure ridge in Normandy when German steel met American engineering and random chance determined the outcome. The final survivors of Sherman blowouts are now in their late 90s or have passed. Their generation is disappearing, taking direct memories of the phenomenon with them. What remains are the records. Maintenance reports describing blown-out belly armor, crew testimonies describing tanks that jumped, technical analyses explaining the mechanical process. These documents preserve the reality of what happened, even as living memory fades. The Sherman that saved its crew by exploding represents a truth about war that official histories often miss. Survival sometimes depends on factors completely beyond control. Skill matters, training matters, tactics matter. But sometimes survival simply depends on which way pressure vents when armor fails, on whether welds break at the right moment, on random mechanical outcomes that align favorably for reasons nobody can predict or influence. The crews who survived blowouts understood this viscerally. They knew they hadn't survived through superior skill or divine protection. They'd survived because their tank's greatest weakness had failed in a direction that didn't kill them. The design flaw had become a miracle through mechanical chance. And they lived because random outcomes had aligned favorably in a combat environment where most outcomes were fatal. 75 years later, the Sherman's legacy is defined by numbers. 49,234 built, 8,000 destroyed, thousands of crew casualties from fire. But hidden in those numbers are the few hundred who survived differently, who experienced the Sherman not as a death trap that burned, but as a machine that destroyed itself to spare them. Their survival wasn't designed, it wasn't planned, it wasn't reliable or predictable. It was just random, favorable failure in a war where most failures were fatal. The tank that saved its crew by exploding did so through accident, through flaw, through weakness becoming strength for unpredictable moments. It shouldn't have worked. By every principle of engineering and design, explosive venting through belly armor represented catastrophic structural failure. But for the crews who experienced it, catastrophic failure in the right direction meant life. They climbed into Shermans every day knowing the risks. They fought knowing penetration usually meant fire. They survived sometimes because the tank failed in a way that directed deadly energy away from them, rather than through them. Not through protection. Through lucky catastrophe. Through the design flaw that became salvation through random mechanical chance. The Sherman was adequate to win the war, flawed enough to kill thousands, and occasionally lucky enough to save hundreds through the same weaknesses that made it lethal. The tank that saved its crew by exploding did so through accident, through flaw, through weakness becoming strength for unpredictable moments. It shouldn't have worked. By every principle of engineering and design, explosive venting through belly armor represented catastrophic structural failure. But for the crews who experienced it, catastrophic failure in the right direction meant life. They climbed into Shermans every day knowing the risks. They fought knowing penetration usually meant fire. They survived, sometimes, because the tank failed in a way that directed deadly energy away from them, rather than through them. Not through protection. Through lucky catastrophe. Through the design flaw that became salvation, through random mechanical chance. The Sherman was adequate to win the war. Flawed enough to kill thousands, and occasionally lucky enough to save hundreds through the same weaknesses that made it lethal. The tank that saved its crew by exploding was all of these things simultaneously. American armor in World War II compressed into a single phenomenon. Engineering triumph and tragic flaw, strategic success and tactical death trap. The machine that won through numbers while killing through design, and occasionally performing miracles through failure. The explosion that saved them was never supposed to work, but it did, and they survived. And decades later, the story remains. The tank that sacrificed itself, the design flaw that became grace, the mechanical chance that determined life or death in a war where survival often depended on which way the pressure went when everything fell apart.